Our next conic that we're going to deal with is going to be the ellipse. So let's start with the definition of the ellipse, similar to what we did with the circle and parabola. The ellipse, if we've got 2 points, we'll call this our focus 1 and our focus 2. Oh boy, those are hard to see. So let's go focus 1 and focus 2. An ellipse is all of the points that will give us the sum of the distances between that point in focus 1 and that point in focus 2. If we add those together, they will always be the same. So this point right here, if I was to add up this plus that, it would be the same as this plus this. If I was to add up this right here, this dotted red line with this dotted red line, it would add up to the exact same amount as the 2 blue lines initially and these solid red lines that I just drew. So that's the definition of what an ellipse is. You might be kind of familiar with ellipses, maybe with some astronomy, with Kepler's laws. If not, that's fine. We're going to go from there. We're going to define these 2 axi as the long axis is going to be our major axis, and this tiny axis right here is going to be our minor axis. So the formula itself is very, very similar to our circle formula. If you remember, our circle formula was x minus h squared plus y minus k squared equals r squared. Well, what if right here, like we had here, we still have a radius, but this radius is going to be different whether or not you're on the major or minor axis. So what we can do is we can divide both sides by r squared, and I'm just doing the derivation of the ellipse, so don't get too confused. R squared divided by r squared is just 1. You have to write this down is what I'm getting at. Y minus k squared over r squared, x minus h squared over r squared. Now we can actually, instead of using r, we can use different values. Let's, instead of assigning this r, let's say our x value is an a and that's a b, we can write, instead of r squared, we can write a squared here and b squared there. So it's very similar to the formula that you've got for circles. You're just going to have slightly different radii. Slightly different radii. They make the distinction between the major axis being our a value and our minor axis being the b value. If that's the case, if you always want to treat the ellipse, the major axis as being a and your minor axis as being b, then you're going to have to be careful with which formula you use. You can see right here that now you're going to have to use the b squared under the h and the a squared under the y. Really what that means is that your x radius is going to have to be underneath the x value. So this is your x radius because it's the horizontal component, right? So if we've got this being our x and up and down being our y, so you can see that, oh, this ellipse is longer in the y. It's more vertically stretched. Then we would say our major axis is the vertical one. We give it a label of a, therefore the a has to be underneath the y. That's just arbitrary. As long as you understand that the x value for the radius is underneath the x and the y value for the radius is underneath the y, that should be sufficient. Identify A, B, and C on the skeleton graph label the center, foci, and endpoints of the axis. Determine the lengths in major and minor axi. Okay, so we know what our A and B are. What's with this C? So C is the final thing that we're going to deal with, and C is going to be what will allow us to find our foci. So if you look back up here, you can see that this is elongated more in the x direction, in the horizontal. So our major axis is cutting right through here. Our foci are always going to be on our major axis. Always. Our foci will not be here and here. That's not going to happen. It's always going to be on the major axis. It's always going to be here and here. So first we have to identify what our major axis is. We find our center, and we're going to move some distance from the center. And that distance from the center to our foci, this distance right here, that's our C value. So how the heck do we find that C value? Well, I could go through the long derivation of it. If I've got some value here, and I had our A value being stretched out, so this, remember, this is our longer point, so this is our A, and this is our B, and this last one right here, I don't want to use that, I'll use the yellow. That's not great either. We'll just use the red in this case. And this is our C. So there is a derivation that we could go over, but really what I'm more concerned about is you seeing that the A is substantially larger than the C. It has to be. The focus has to be inside the ellipse in this case, right? So the A has to be larger than the C. Well, this is sort of, and then the derivation, it would make a little bit more sense, but we're going to find our C using Pythagorean's theorem, such that we would get that it wouldn't be A squared, it would actually be, in this case, B squared plus C squared will give us our A squared. So if we wanted to find our C squared, it would be A squared minus B squared equals C squared. So let's look at our graph. Our first example, we have to compare it to x minus h squared all over a squared plus y minus k squared all over b squared equals 1. Do I have an h and a k? No, because of this x squared and y squared just being by themselves, our x and k are 0, 0. So we know that our center is going to be at the point 0, 0. Our a, well, if a squared equals 36, our a will equal 6. Our b, if our b squared equals 4, the square root of 4 is 2. How do we find our c? Well, we plug it into this Pythagorean theorem, and we get that 6 squared minus 2 squared equals our c squared. So 36 minus 4 equals c squared. 32 equals c squared. And we square root both sides. And we get the square root of 32. So where is our point C? Our point C is going to be from our center, which is at 0, 0. We will go over, because our C value is a square root of 32, he's going to be, he's on a y value of 0 because our y hasn't changed, but our x has gone over a value of square root of 32. What about this one over here? Well, you go 0 and then you go left square root of 32. But our y is still 0. So that's how you're going to have to identify your center, your A, your B, and then finally your C so that you can find your foci. So let's go over here, let's do a few more. Our center here is going to be at the point 3, -5. Our A, which is our major axis, is going to be the square root of 49, which is 7. Our B is the square root of 9, which is going to be 3. And our C, remember that C squared equals A squared minus B squared. So 49 minus 9 is 40, so C squared equals 40. So C equals the square root of 40. So now we got everything that we need to plot these points. Our center right here is going to be at the point 3, -5. We know that our A is 7, our B is 3, and our foci are going to be at the points. They're going to be like right here and right here because they're on their major axis. So we're going to go to the right square root of 40. So this will be 3 plus the square root of 40, but the y value is the same. This will be 3 minus the square root of 40, but the y value is the same. That's how you break up that one. This one is going to be where our y is favored, where our y is our major axis. Again, our center is going to be at -1, 8, based off of these values. Our A squared equals 100, so our A will equal 10. A is our bigger one. Not necessarily that it's under the y, it's just the bigger axis. B is the square root of 16, which is 4. And our C is going to equal, remember our C squared is equal to A squared minus B squared, because our C is just inherently smaller than our A. That's going to be 100 minus 16, which would be 84. So if I square root both sides, I get the square root of 84. So let's go to labeling this ellipse. We know that our center is at -1, 8, and our foci are going to be on the major axis. Now my x value doesn't change, so it's the x value of -1. It has gone up square root of 84, so it's 8 plus the square root of 84. And then this one is -1, and it's 8. It's gone down, 8 minus the square root of 84. This final example will be to, oh, never mind, this is not the final example. Example 4, first, we're going to have to find our center. So our center is -2, 2. Our A is 1, 2, 3, 4, 5, 6, 7. So he's gone over 7. And our B is 1, 2, 3. So if I was to make this equation, our x is the longer axis, is our major axis, so it's going to be x minus -2, which would be x plus 2 squared, all over a squared, which is 49, plus y minus 2 squared, all over 3 squared, 9, equals 1. Put this equation in standard form. Well, it's not equal to 1, is it? We always have to have this equal to 1. So, how do we get there? Well, I see this isn't equal to 1, so the easiest way to do that would be to divide everything by 64. When I do that, 4 divided by 64 is going to be 1 over 16. We're going to pull a 4 out of both of those, and we'll get x minus 11 squared over 16 plus y minus 5 squared equals 64 over 64 equals 1. Now we're in our form that we're familiar with. We can see that we've got a center of 11, 5. We have an a value. Our major axis is right here. Our a squared is 64, so our a is 8. Our b is, the square root of 16 is 4. And we could also still find our c. Remember that our c squared equals a squared minus b squared. So a squared minus b squared would be 64 minus 16, which would be 48. So if we square root both sides, we get c equals the square root of 48. They didn't ask that, we won't graph it, but I wanted to show you that you could derive everything pretty simply from that formula. So it's a lot of information, but it still is just a small modification on our circle formula. If you can remember these, you should be good.